Alright, so what I'm going to do for you, Sid, here is we're just going to look at some of these concepts and going to build up. And so I use the idea of a gravitational field, just so you're not thinking in electromagnetic charges. And there were some equations we had before and some geometry that we knew. And what's happening is field lines exist. They flow through space. If you ever get a chance, watch the new Cosmos, and they do a good job of kind of thinking about how Faraday imagined the flowing field lines. But let's look at, I'm just going to make a uniform electric field somewhere in space. And so to do this, I'm just going to make some field lines here. And we're going to talk about what the field lines do. Now, I don't have a grid system down here, so I want you to imagine that I am drawing a little bit neater and that these are evenly spaced field lines. So the field has equal strength wherever in space. And we have a parallel field, and it has a set magnitude. Right? Here's some E field, and we'll give it a direction because field lines have a direction. And so we're building our way up to Gauss's law. We'll say this is three-dimensional space, but we're near something. And I hope you can appreciate we will find certain geometries that create even field lines. And I'll say this is near a parallel plate, right? And so we have these flat field lines. Well, if I want to represent some area in the middle of this, and we'll say here, and I look at the field lines coming across. Now remember, topologically, I can transform the shape into any shape I want that's enclosed. So I'm going to pound this circle down, and I'm going to pound it into a square. I'll make a yellow square here, and so we'll say we have a square. Now the thing that's going to be about this square and the circle, now geometrically I didn't draw this that way, but they have the same perimeters, right? The circumference of the circle is the same as the perimeter of the square. Now the geometry of this will be slightly different, but I just want to say that the same thing is happening. And what Gauss is alluding to with these surface areas and these areas of enclosed spaces is that we can talk about the length around the side or the area coming across. Now, what's interesting about this is the field line that strikes this side, right? Neither goes in or out of it. It rides right down it. Well, the field line that rides this one doesn't strike in or out of it, right? But, so I'll put a little white check on these, right? They're not going in or out of our enclosed surface. And on this side of my surface, I have 1, 2, 3, 4 field lines coming in. So I have positive 4 field lines going in. And over here, I have 1, 2, 3, 4 field lines going out. So I have negative 4 field lines going out of my enclosed surface. And so the net effect is there is nothing inside. Well, the same thing happens for the circle, right? We know that if we use our law of flux, we'll have to take the angle this makes with the surface, and we can do the same thing here and the same thing here. But the amount of stuff coming in is equal to the amount of stuff going out. And this tells us there's nothing in the middle. Nothing to create field lines. And so we're going to use empty space to show that example. And so what Gauss's law is hinting at is if I have field lines and I enclose somewhere in space, if I have more things going in or coming out, there has to be a source in there. And so if we look at empty space and that there is the equal amount of stuff coming in and out, well, this says, hey, enclosed in here, there is 0 charge because it doesn't generate the field lines.